So hi everyone, I'm Varun. Welcome to our presentation on the distributed song recommendation system using Apache Spark. I'm Varun and I'll be introducing our project today. Our team consists of Abhilasha Senapati, Avinash Nandyala, Tanvi Agarwal and myself, Varun Panigrahy. So coming to the project overview, so the goals of our projects is that music streaming platforms like Spotify and Apple Music process billions of user interactions daily to provide personalized recommendations. Our project addresses the challenge of building a scalable recommendation system that can handle large-scale datasets efficiently. We chose Apache Spark because it's designed for distributed data processing and provides the scalability needed for real-world recommendation systems. So the main goals of our projects were threefold. So firstly, we wanted to implement a complete data pipeline that can ingest and pre-process the million song dataset, which contains over 48 million user song interactions. Secondly, we aim to build and validate an ALS collaborative filtering model using Spark MLlib. And thirdly, we set out to benchmark the performance differences between a single executor and multi-executor Spark configurations to demonstrate the benefits of distributed processing. So coming to a brief overview about the dataset. So the million song dataset provides a rich collection of user listening behavior. Our dataset, which is in the file called trained.triplets.txt, contains tab separated records with user IDs, song IDs, and play counts. So initially we did the cleaning and pre-processing, and we were left with about 48.3 million clean song interactions. For our benchmarking experiments, we tested on subsets ranging from 100,000 to a million interactions to analyze scalability patterns. Now let me hand it over to Abhilasha to go over our next system architecture and the data pipeline design.
Thanks, Varun. I'll be discussing the overall high-level system architecture and the data pre-processing pipeline. Our system is built on Apache Spark 3.5.1, and we have run it on Google Colab. We have simulated both single node and multi-executor configurations. Um, if we go through the high level architecture of our system, it follows a layered approach. At the very top, we have the data source, that is the million song data set. This is then fed into the Spark ingestion layer, which uses PySpark to read and parse the tab separated data. Next comes our pre processing pipeline. This pipeline performs critical data cleaning operations. Finally, we have all this cleaned and parsed data fed into the ALS model training layer, which generates the personalized recommendations for us. The key advantage of our architecture is its modularity, where each layer is optimized independently and works independently, and the entire pipeline is designed to scale horizontally when deployed in a true distributed cluster. If we go to the data pipeline details on the next slide, can we switch to the next slide? Yes. In the data pipeline details, it consists of 5 main steps. First is parsing, clean, transform, index, and split. First, we load this raw data using Spark's CSV reader with tab separation. Second, we clean this data by dropping the null values and filtering out certain invalid play counts and invalid entries. Third, we transform this clean data to using log 1p normalization, which converts the raw counts into a more suitable rating scale. Fourth is we use Spark's string indexer to convert user and song IDs into numeric indices required by the ALS algorithm. Finally, we split the data into training and validation sets with a 90 to 10 split. This pre-processing is very important because it ensures the data quality and prepares the data in a certain format that is required for the machine learning model that is being used, which is the ALS model in this case. We have implemented two Spark configurations. Let's move to the next slide. We have implemented two Spark configurations, the multi-executor and the single executor configuration. The multi-executor setup uses the local asterisk, which leverages all the available CPU cores for parallel processing. And the single executor configuration uses local 1, restricting execution to a single core. This allows us to directly compare the benefits of parallelization. Now, I would hand over it to Tanvi, who is going to explain our ALS model implementation and how it generates the recommendations.
Thanks, Abhilasha. So I'll be covering our ALS model implementation and how it generates personalized song recommendations. So ALS stands for alternating least squares, which is basically a collaborative filtering algorithm that's particularly well suited for implicit feedback scenarios like ours, which is music streaming. Now talking about how ALS works. It works by factorizing the user item interaction matrix into two lower dimensional matrices. One of the matrices represents the user preference and the other represents item characteristics. So the algorithm alternates between optimizing these two matrices until they converge. And for our implementation, we use implicit preferences, which means we treat play counts as signals of user preferences rather than explicit ratings. Now going over the model parameters that we have set, we set the rank to 16. The rank of 16 means we use 16 latent factors to represent user and item features. Then we also have the regularization parameter set to 0.1, which is basically to prevent overfitting. And then we use an alpha value of 40, which is to scale the confidence in implicit preferences. And we have limited training iterations to 5. This is basically for efficiency. Um, can we move to the next slide, please? So talking about the model training and model validation processes. So during training, the ALS algorithm processes our pre-processed data in a distributed manner. So this it does by partitioning the data across all the available executors, and this allows for parallel computation of matrix factorizations. And post-training, we generate recommendations in two ways. First, we get the top K recommendations for all users. Second, we can also get recommendations for specific user subsets. Each recommendation includes an item ID and a confidence score, which indicates how strongly we believe the user will like that song. Now, talking about the model validation phase, we validate our model using a held out validation set, calculating the RMSE on the predicted ratings. So from our validation, the RMSE VC is 1.2 on the log normalized ratings, which indicates a reasonable model performance. The model also handles cold start scenarios by dropping predictions for users or items that we don't see during training. Uh, Now I'll hand it over to Avinash.
Tanvi, I'll be presenting our performance benchmark results and the key insights we have gained from this project. Our benchmark experience compared single executor and multi-executor configurations across 4 different datasets. Our results clearly demonstrate the benefit of parallel processing for the multi-executor configuration. Training times were 94 seconds for 100K and 112 seconds for 300K, and around 113 seconds for both 500K and 1 million. In contrast, the second single executor configuration took approximately 206 seconds for 100K interactions and 213 seconds for larger datasets. It represents a roughly 2x speed up when using multiple executors. The multi-executor setup consistently outperformed the single executor configurations across all datasets. Increasingly, both configurations showed a similar pattern. Training time increased from 100K to 300K interactions and then plateaued for larger datasets. This suggests that beyond a certain point, other factors like I/O or algorithm overhead became the bottleneck rather than the data size. So the key findings are as shown before. I've talked before, and then uh, several important insights emerge from our analysis. Firstly, the parallelism matters significantly. Using all available CPU cores provided substantial performance benefits. Secondly, Spark configuration settings, particularly the number of executors and shuffle partitions, have major impact on the performance. Third, caching intermediate data frames is crucial for iterative algorithms like ALS, as it avoids recomputing the same data multiple times. We also identified limitations of our single node collapse simulation. While local asterisk provides parallelism, it doesn't capture the network overhead, internode communication costs, or fault tolerance mechanism of true distributed cluster. However, it effectively demonstrates the benefits of parallel processing on a single machine. And then I already talked about the key insights. And then the conclusion. In conclusion, we successfully built a scalable recommendation system that processes millions of interactions and generates personalized recommendations. Our benchmark demonstrates clear performance benefits from distributed processing. For future work, we plan to deploy a true distributed cluster, extend to full 48 million interaction datasets, and add content-based filtering capabilities. Thank you for your attention.